Okay, welcome to the next colloquium in the hottest summer school. Today, I'm very happy to introduce Favonia, who will be talking about Cartesian cubical type theory. Now, please go ahead.
Hi, so I'm Favonia. So by the way, just to let you know, I cannot see your face and whatever. So please follow Dan's instructions to ask questions, and also feel free to just use the chat or whatever mechanism you feel comfortable to interact with others. Okay, so today I would like to talk about Cartesian cubical type theory. And before doing so, I would like to review some basics of cubical type theory that you might have already known if you have attended the latest Agda lectures on Cubical Agda. But so I assume that most of you probably have already some ideas about what I'm going to say in the next, say, 20 minutes, but I think it's still very important to go through them once again. So cubical type theory is an extension of the multi-level type theory by introducing something called interval in the context. So what it's doing is to enable us to talk about like lines, squares, cubes, or even n-dimensional cubes where n can be arbitrarily large. So when there's only one interval in the context, as shown in this diagram, it means that the term is really a line indexed by this interval. So as you can see on the screen, there is a I here in the context. So I represent some unknown point in the interval. So in the type theory, usually we only have you're able to pinpoint 0, pinpoint 1, and you can say that there's something in the middle, but you cannot say, for example, 0.3. So you cannot name a particular specific point in the middle. You can only say that there's some point in the middle, unknown, abstract point. So the term m here, oops, let me erase this. The term m here is indexed by I. So you can imagine that it means that for every I unknown point I in the interval, there is some term here. So together, it will form the line from 0 to 1 like this. So the type is A, and also the type is also indexed by the I here. So there's a dependency on I for both n and A. Okay, so this is kind of boring because there's only one interval. So if we have two intervals, it means that the type itself is a square and the term itself is also a square. And the I and J here, they form more like a coordination system. So for example, if you have I here, like in this direction and the J in this direction, for any particular I and J, it means that you are actually locating some point in this square. And for this point, there's also a point here. And so that will be the term corresponding to this pair of I and J. So together they form a square by considering the entire square, like spanned by this interval in this direction, the I direction, and the interval in the J direction. Okay, so you can imagine that this process can go on forever. If you have 3 intervals in the context, then you will have a square, and also the term and the ties become the square. And if you have 4, then it becomes a hypercube. And we have 5, I don't know the name of it, but anyway, it will be called 5 cube. So at some point, mathematicians are getting tired of naming this hypercube. So it just becomes 5 cubes, 6 cubes, 7 cubes. And believe me, for every practical purposes, you're only going to handle 4 cubes. If you have to handle 5 cubes, either you'll be stuck or Agda will be angry at you. Okay, anyways, so let me move on. So one important thing about these cubes is that you can get subcubes of them. For example, if you have a square in the middle of the screen like this, so you can get a line in the back in the I direction. So that will be m with I for I. Excuse me, m for with 1 for I. So that means that the one end in the I direction. So that will give you the back edge. All the other side will be m with 1 for j. So that is getting the one end in the j direction. So in the cubical agda, you probably have seen like 4 sides of this square, which is 1 for I, 1 for j, 0 for j, and 0 for I. In the Cartesian cubical type theory, this variant I'm going to talk about today, we have something new. We can also get the diagonal directly, which is the I for j. So I'm going to talk about this a bit further. So let me step back a little bit. So in cubical agda, you can still have this substitution I for j everywhere. So the diagonal I'm talking about is that even when you are doing the composition, you can specify the diagonals. Okay, just to repeat, to kind of clarify some of the thing I might have misled you. The substitution for I for j or 0 for j or 0 for I, this works for cubical agda and also the variant I'm going to talk about today. But the diagonals will play an important role in the thing I'm going to introduce later. Okay, so this is my very quick overview of the basic ideas of the cubical type theory. And today we are going to focus on composition and coercion, and also the intervals. All right, so this is an interval, the algebra on the interval, to be precise. So we have already seen that if there's I representing some unknown point in the interval in the context, then I is an interval. So there's no problem with that. And 0 is an endpoint, and 1 is an endpoint. So I'm showing you the kind of the formal logical rules of what counts as a something in the interval. So in the cubical agda, you have something additional. So for example, you have this and, the meet, and the join, and you also have the this tilde representing the reversal. So in the variants I'm going to talk about today, you don't have any of this. Okay, so you only have I as the variable and 0 and 1 and nothing else. So this is the first major difference I want to show you from the cubical agda. So in cubical agda, if you have 2 things in the interval, you can take the meet, or you can take the join, or you can take this kind of reversal funny symbol like tilde. But in the variant I'm going to talk about today, you only have variable 0 and 1 and nothing else. So these 3 things in the bottom will not be available today. Okay, so let me move on. So before talking about the composition, which we will spend lots of time on it, I would like to step back and give you some ideas about like what's really what's cool about cubical type theory in some sense. So in the homotype type theory that you have been studying for a while, in the at least the original representation, you have a type A, and you want to add something new to it to make it higher inductive. For example, the univalence. In a sense, you can treat the universes as the high inductive types where the univalence is the path constructor. So you kind of want to make things higher inductive, make a universe high inductive in the sense that to make it univalent, or having the circle type or some torus type or other types. So in the non-cubical homotype type theory that is written down in the hard book, so you don't have a mechanism to add those paths directly into the type A. So A is something that we want to throw in some new passes. So how can we do that? Well, we have the identity type, which is the internalization of the pass in A. So instead of adding things into A, you add things into this IDA directly. So you just assert that there is a path or identification called univalence in the universe, or loop in the circle, or function intentionality in the function type. So you just add those things in the ID type. And due to how type theory works, the thing you add here will somehow indirectly influence the type you begin with. So that's how it works, but it leaves something undesirable. For example, something will not compute, etc. So I don't want to repeat the point. I'm just saying that this kind of works, but it's not ideal. All right, so this is what's happening before the introduction of cubical type theory. By the way, if you have any question, please don't be shy. Just throw in the question, because I expect that you'll ask some question. Actually, I reserve some time for you to ask questions. So if you're not asking, then you are wasting your opportunities. All right, so let me move on. By the way, I just want to double check that. Dan, can you hear me?
Yes, I can hear you fine.
Okay,
Everything's
because
great.
it's kind of strange that I'm talking to a silent room. Something that I can never get used to for Zoom. All right.
So a question just appeared in the chat. So since I'm unmuted, why don't I read it out? It says, how is this induced relation on the original type generated? Can you elaborate a bit more?
You mean this? Okay. So let's see. So in the let's take circle for example. Actually, circle is not okay. Let me take the univalence for example. So univalence can be treated as a past constructor of the new universes we want to create. So A here is a universe, some universe, like say in the first universe, like U naught. And the ID U naught is the path space or path type of this universe. And then by adding the univalence in it, say again? I think I heard something, but I didn't hear it clearly. Okay. Did I miss something?
Sorry, just go ahead. I think it was an accident.
Okay, all right. Let's see. So univalence can be treated as a past constructor of this IDU, where U is some universe. And then by adding this, you are adding axiom saying that, okay, right now, magically, there is a path in the universe induced by this, by the equivalences. And somehow this will influence the U. So the influence, like by using the word influence, it sounds like it's an action, like somehow this axiom is attacking the original type or changing the original type. But that's actually not what's really going on. You have to consider the type theory of all the influence rules, etc., as a kind of entire thing. So what I mean is that it's not that you have the original type theory and somehow magically you can add this axiom and that is influencing the original type theory. The moment that you're adding the axiom, the moment that you are throwing a new constructor, the entire type theory has been changed. It's a coherence conditions or kind of the coherence condition will make it always coherent. So there's no process of changing. By adding things in it, everything will change immediately. And the universe will be changed to have these new passes. Okay, I'm not sure if that answers the question or clarify anything.
Yeah, it's good, he says.
Okay, so as I said, this works. I mean, you can prove meta theorem showing that, okay, this makes sense. It has great models, and we can do a lot of things with them. But it lacks the computational properties that we want. So in a sense, it works almost by accident, I would say. Okay, anyways, so let me move on. So the problem of the previous approach is that when you're adding new things to the ID type, saying that, okay, now there's a new path in the universe, which is called univariance. But when you are handling and some element from the type, say from the universe, it has no idea what kind of garbage you have thrown into the ID, whatever type. Saying that, for example, if you're throwing the loop as a path constructor to the ID of S1, but your rules, the elimination rule is for the S1, how would the elimination rule knows that, oh, you're just throwing some garbage into some ID S1 or some IDA for some type A. So this kind of this is a problem because there's some new things added into ID of something which is different from A. So IDA is different from A. So you're kind of internalize the path in A as IDA, and then you're throwing something extra in the derived thing, and you expect the original thing to magically know that, okay, you have changed the derived thing, so I have to also act magically to deal with them. So that just from the even from the very beginning, from the philosophical point of view, it will not work because that's very strange. So the cubical type theory is changing the entire method. So instead of adding things to the IDA, which the original type A has no ideas about, it adds things into the type A directly. So now the loop constructor is part of the circle directly. It's not through ID of circle. It's in the circle type directly. So you're adding the new path directly in A. So the type has full control of these new passes and also has the full information about how to handle these new paths. And that's basically the core idea, one of the core ideas to make the cubical type theory compute. The circle type now has full information of the loop constructor. The universes have the full information about the univariance. So you can specify how to deal with new passes generated by the new path constructors directly in it. Okay, so this sounds very cool, but it then induces lots of new questions. But let me put the question aside because I have another thing that I really want to clarify, which seems to occur lots of time. So we have seen the path types, which is basically internalization of some elements indexed by I. And we have seen the identification types or identity types, which basically is something freely generated by the reflexivity from the homotype type theory. So people often say that, okay, if you interpret the identity types as the path type, then you will not have J. That is technically correct, but that's misleading because in cubical type theory or any type theory which supports paths and identification types, you can actually have both. So if you interpret one type in terms of another type, then, well, they are different types. So a priori, they might not be really the same, even though there's some research trying to make them the same, but I'll stop here. But a priori, they have different definitions. One of them is the internalization of the hypothesis the interval in the context, and one of them is freely generated by the referral. So they are different, and they can coexist in the at least in theory. For example, in rectitude, we can have both. So if you're not interpreting the identification types as pass type, but instead just interpreting the identification types as identification types, then you will still have J. So I just want to clarify this point. It's not that you have to use pass types in the cubical type theory. You can still have a different type, which is called identification type, and you can interpret the identification type in the homotypic type theory as identification types in the cubical type theory, and then the J will still hold. Anyways, so I thought there would be some questions here, but anyways, so please interrupt me anytime. So I will just move on. So going back to our new paths business. So the cubical type theory says that, okay, let's not change the IDA directly, but instead just throwing in new passes in A. But then it becomes a problem because the issue is that we might not throw in enough passes. Saying that the A is a circle here, and we are throwing in the loop as a pass constructor. And one of the immediate issue is that, well, in the homotypic theory, we should know that you can concatenate two passes, right? And for example, here you should be able to concatenate two loops to form a new pass as kind of a continuation of, like, you can travel through a loop and then travel through a loop again, or maybe like 3 times or the arbitrary number of times. So that would be a concatenation of n loops, or you can also go around, for example, the reverse of it. However, a priori, if we're just saying that there is a loop as a pass, nothing forces the existence of this additional pass induced by this new pass that we think that they should exist. So for example, here on the screen is a very simple example. So if you have two loops putting together, there should be a new pass representing the concatenation of these two loops. But nothing right now like forces the existence of this. So we need to do something extra to make them exist. Okay, so, and this is why we are talking about the composition and conversion or together called Kahn operators. So in the multi-level type theory, or usually dependent type theory, in order to talk about the type, like circle type, sigma type, function type, or whatever, usually it has a few elements. First of all, what is the type? So you need to specify how to write down the type. For example, there's a type A and type B. Then A to B is a type, and we call it a function type. So you have to say that, okay, there is a function type like that. And what other constructors? For example, for function type, you say that you can use lambda abstraction to construct a function. So that will be the constructor. And then how to consume the element or how to eliminate the element. For function types, it means that, okay, you can apply the function to say argument to get a result. So that's how you use or consume an element. So that's called elimination rule. And then the fourth thing will be like what happens when a constructor is consumed in the function type. It means that what happens if you have a lambda abstraction applying to the argument. Well, then you should do the substitution, right? You should substitute the argument inside of the body of the lambda function to get the result, to basically evaluate the body of the lambda. So that's the beta rule. So the beta rule for the function is to do this substitution. And you can also specify the beta rule for other types. And some types also have some property of the uniqueness. So it means that every element of that type is judgmentally generated by one of the constructor. So this holds for function. You can say that every function is can be written down like judgmentally written down as a lambda abstraction. So now, so this beginning phi is what you should have known if you have looked at the homotopy type theory lectures. And now we have a new thing. We have a new thing to make sure that we have enough paths in A. For example, the concatenation of two paths or reversal of the paths. So the sixth thing is basically why you need the coercion and the composition and other things. Okay, and together we call it Kahn operators, named after a mathematician, the mathematician Donald Kahn. Okay, so that's why we need this.
So
why?
Can I ask a question from the chat?
Sure.
And I think this is a bit more related to the previous slide, but I wanted to wait for a little break. The question is, can you prove things about identity types and then transfer that proof to proofs about path types? Oh,
okay. So that's a very, very good question. So the question is, if you have already approved using the identification types, can you just transform that into a path type? The answer is yes. In particular, you can prove that identification types given 2 points in the type, and you can form identification from A to B being a type. And for the paths, you can also do the same thing. And you can prove that these two types are equivalent. So by univalence, there's a path between these two types, so we can just transform them. So the answer is yes. And there's a very generic constructions using univalence. Okay, does that answer the question?
Yeah, so then, but since we have compositions for identity types, that might suggest that you can prove compositions for path types.
So I see. So the question is that, so that's a very good question. The question is that if we have both, and the things identification type seems to have good properties, then we should be able to transfer the good property into the path types. So I would like to go back to this diagram a little bit. So the identification type is a internalization of the type A in the new framework. So if we don't have the extra structure that I talk about in A, you actually are not able to even have a well-defined. Let me see how to prove how to say it. So right now I'm kind of talk about this construction as a step-by-step process. But as I said, every step is not just changing something locally, it's changing everything globally. So if you're not adding, so in the middle of adding the sixth component, which enables a particular A to have enough paths, before doing that, which is kind of weird statement because you actually cannot do it. So what I'm saying is that if your type theory doesn't have this extra structure, basically it's entirely broken. You cannot really have a well-behaving ID.
Okay, I think that's good. We'll let you go ahead and explain the Kahn operations.
Okay, so I'm kind of trying to motivate why we put these pieces in the type theory and not pieces in the type theory. But every change is actually a global change. So before doing that, and then you will not really have something that is globally working. But I think I will move on. But this is a very interesting question, and I encourage everyone to think about this, because it's actually more interesting to know why than just learning what it is. Okay. So, all right. So I hope I have motivated enough that why we ever care about this composition or whatever operations that we need. So I want to set up some terminology I'm going to use because I realize that even the experts in this field have been using all kinds of strange, different terminology. So I'm going to call this vertical things faces or walls because they are kind of vertical, and then the bottom thing is a cap. Okay, why is the bottom thing cap, not the other way around? Well, just just live with it, okay? The bottom thing is a cap, and then there's a type in the bottom. So if it is the first time you're seeing me drawing this diagram, you might be confused. What's the relation of this bottom line and the cap? No, okay, that's the wrong way to see this picture. So the square above, so this is a term. So the thing I wrote down is a term. Okay, this entire thing is a term, like n. And then this is a type. So the bottom thing means that, for example, this face, the entire face is this type. So you can imagine that there's a point in the entire type line. So this is a particular type here, and the entire face is lying over this point, which means that the entire face actually has the same type, which is the type here. And the cap, different point in the cap can have different types, like depending on where you are. For example, the point here has this type, and this point has this type, and this point has this type. And the face on the right, they all have the same type on the bottom. Okay, so the type is not changing vertically. So everything, like no matter how high you are, you have the same type. Only when you are moving horizontally, the type can change. So this is called homogeneous composition, or HCOM. I think HCOM is actually a very terrible name, because how do I know that H doesn't stand for heterogeneous, which will be the opposite of homogeneous? I mean, and H can also mean lots of things, right? It can be homotopic or higher, like who knows what it is. But anyways, I think it's already too late for us to change the history. Unfortunately, we have already settled with the idea that H means homogeneous, okay, means the same. So what is being the same? When you're moving up and down, the type will not change. So this point, this point, this point, this point, like if you move just vertically, the type will not change. So this is a homogeneous composition. Okay, so going back to this diagram. So it means that if you have the faces and the cap, somehow this operator will give you something at the top, the dotted, the dashed red line. So this is the thing you can get out of this composition. So by the way, today I'm not going to write down the term, because I think that is not really helpful in terms of conveying the intuition. But if you are confused, you're saying that Favonia, I really, really want to see the Agda code somehow. I can write it down for you. So just interrupt me. Okay, so this is a homogeneous composition. And so we are going to focus on this for a while. So this is a 3D version. All right, so I like 3D because that's almost the limit I can do on the screen. So the type is now a square. So being homogeneous means that when you're moving up and down, like vertically, the type will not change. The type at this point, at this point, this point, this point, this point, this point, everything like vertical on this point, they all have the same type here, like in the bottom. So you can just look at the projection of the entire cube into the ground, on the ground, and their projection on the ground will be the type. Okay, so the type is kind of the basis of the foundation or the ground or whatever, like whatever thing that whatever analogy that works for you, Okay, so the top thing is what we get. So I'm going to move on because I want to show you something cool. So in Cubical Agda, you know that is just one possibility. You can omit one of the faces. In the two-dimensional cases, you can omit, for example, you don't have to specify this, you only have to specify one of them, or maybe on the other side, or even nothing at all. So for the square, you already have 4 possibilities. And let me show you. And usually it takes a while to load this. Oh, okay, it's immediate. Cool. So if it's the 3-dimensional cases, then you have 16. Because you can choose to omit whatever faces that you have from 0 to 1. Okay. And if you think about it a little bit, then you can easily derive the formula like 2 to the 2n minus 2, where n is the entire number of dimensions you will have. By the way, you should not just believe me for arbitrary formula I just throw in at you. You should at least try to check why this is even the case. Okay, so but I'll move on. If you're curious, please check. So in the Cartesian cubical type theory, excuse me, I forgot that I just added a new slide here. So there's one thing that is important that you probably have already known, but I still want to repeat that. When we are trying to design these shapes, there's one thing that's important in the type theory is that we want to make sure that the composition commutes with substitution. So substitution in cubical type theory, as we have talked about earlier, is basically taking a subcube of the entire thing. So here, on the left-hand side, you have a composition problem, but you are omitting the right and left faces. So you only have the front face and the back face, and you have the cap here, and then you can get the top. So substitution, if you pick the correct 0 and n and the correct direction, you can get this right hand side part. Okay, so if you look at this, it's actually a composition problem itself. So it has a cap here, it has two faces, like this, and then you are getting the top of it. So if you just turn this a little bit, so it's actually a composition problem itself. Okay, and the type theory requires that if you can do this full composition first, and then get this part of the red part, and it should be the same as getting the individual parts from the faces and cap to form this problem, and then get this red diagram. So these two things should be judgmentally equal. So it shouldn't matter whether you are doing the substitution first and then getting the and do the composition, or do the composition and then getting the subcube. So they should be the same. So when you are designing, so this is one of the tricky part of this composition problem, and that's why in some of the original papers they call it uniform. So uniformity is to make sure that this condition holds. Everything commutes with substitution. So okay, I'm going to move on to show the cool thing. Okay, so in the Cartesian cubical type theory, we have we can specify diagonals even during the composition. So this is not possible in the Cubical Agda, but something we have to do in the Cartesian cubical type theory. So this is probably the kind of the most normal one, and then you can omit different things, but you can also have this diagonal. So this means that okay, I have a U shape with the two faces in the bottom, but then I can also then I don't care about the top line anymore. I want to say that okay, please give me a diagonal here, and then you can also omit other things like this, and you don't have to end up with a diagonal. You can also start with a diagonal. For example, what is this? It means that you have a face here, and the cap itself is a diagonal, and then you want to get the top line. So you can go from diagonal or to a diagonal. So in the two diagonal cases, if you believe me, there are 24 cases. Okay. No one asked any question. Okay. You shouldn't just believe me, like whatever numbers. Okay.
There have been some questions in the chat, but
okay,
so far,
please.
So far, I've been fielding them, but there's one right now that I could ask. So the question is, are the diagonals replacing the role of fillers since we don't have meet and join on integral coordinates anymore?
I see. So that's a good question. I'm actually going to, you're spoiling the fun. Okay, but the answer is yes. And then well, maybe I should say partially. The diagonal can be used to create fillers out of this composition. And we're going to talk about this if you couldn't see it. The diagonals also play an important role in making the univalence, making the universes univalent. So during the construction of the glue type that you probably have seen in the Cubical Agda, in the Cartesian Cubical Agda, since we don't have meet and join other gadgets, we're using the diagonals to basically to achieve the same thing. So filler is one of its function, one of the results you can get, but you can also get other cool things. And it was originally motivated by making the universes univalent.
Okay, sounds good.
Okay. Oops, I think I made a mistake. There are two kinds of diagonals. The diagonal I show you here, I think I have to remember the history. I think it was originally motivated by the filler. So the person who asked the question is correct. There's another diagonal that I'm going to show you, which was motivated by making the universe univalent. So please let me correct myself. The answer to the question is yes. This is motivated by the filler, and we will see a different kinds of diagonals, which is motivated by making universe univalent. So together, diagonals have multiple purposes. Okay, I think that's the correct answer. I should have drink more coffee, not just water. All right, so let me move on. So for the 3D cases, so this is an interesting part. So you can also have the diagonal as a result. So the red one is the final thing you want to get. So you can also from the top to down. Oh, I probably forgot to say this. So you can go from 0 to 1. So this already in the previous diagram. So for example, this one, the cap is really the cap in the at the top, and then you want to get the bottom. So you can also do the same thing. The 3D cases, you can also get. Okay, this is a bit tricky. I'm not sure if you can pause this. So you have this diagonal, and you want to get a diagonal in a different direction. Okay, so you can go from diagonal to diagonal since you have more dimensions now. So there are different kinds of diagonals, and that's also fine. And the interesting thing I want to show you is here. So you can have a diagonal constraint here. Not sure if you can see it. So this one is kind of here. So this is not possible in the lower dimensions, but with three dimensions, you can see this. So this means that I can also have something still vertical, but itself being a diagonal. Okay. So and I want to get a bar. Okay. I don't have energy to draw all the 3D faces. Someone have to pay me a lot, I guess, to draw all the cubes. But I want to throw just some random question at you. How many are there in the 3D cases? Is this formula correct? Like I thought something. So let me explain this formula a little bit to make it a little plausible. Well, at least for when n is 2, like 2 to the n minus 2, so this 4 times 3 times 2, so that is, excuse me, yeah, so that will give you actually, no, 4 times 3 times, yeah, 4 times 3 that could give you 24, which will match the number of this. So when n is 2 is correct. So Dan or whoever that is, who is the host, can you start the polling?
Sure. Okay.
So the question is, do you believe that this is a correct formula?
I think I need to restart it. Here we go. Relaunch poll.
Yeah, please relaunch it.
Okay. So can you repeat the question?
Okay, the question is, so how many are there for different combinations? So in the two-dimensional case, we see that there are 24. And n will be the kind of the total dimensions we have. So the formula is correct when n is 2. Is this the correct formula? So let me explain a little bit like why we're going to put this. So the 2 to the n minus 1 minus 2 is basically the number of the things we will have in the cubical agda, because you can decide whether you want this phase or not. And then the n plus 1 here and n is basically n choose 2. Excuse me, n plus 1 choose 2. And this means that because you have the top and down, and you also have different kind of diagonals in the middle, right? And if I go back to this, you basically have 1, 2, 3, right? So you're going from, for these 3, the Z shape, you're going from one of them to another one of them. So so you could have 3 choose 2. So that would be n plus 1 choose 2. Okay. Questions? If you have a question about the question, you should ask.
Okay, so one question is, do all the diagonals in the n-dimensional case have to be n-dimensional, or can they be lower dimensional?
Oh wow, that's another excellent question. So the question is like, do we have to always be n-dimensional? In the quantity, the answer is no. So you could, for example, when you're doing the composition in the here, you could potentially only have a kind of vertical pole, which is kind of just a line there. So instead of having an entire thing, you only have this line and not this. Okay, and that's fine. That's fine. But for counting purposes, I mean, because this will add so many of them. For counting purposes, let's just assume that every phase need to be kind of 4. And to make it counting easier, we also doesn't include the cases where the starting, the cap is exactly what you get in the end. Because if you look at the formula, there are some degenerate cases where you can start from the 0 and then to the 0, but that is really boring because so that's why I didn't draw it out. Otherwise, you will have more variance here. Okay, so for counting purposes, the cap cannot be the same as the end, and everything need to be 4.
Yeah, I have to admit I don't quite understand the constraints.
Okay.
In the picture you just showed, you don't have anything with 5 faces shown.
Mm-hmm. So okay. I guess if Dan doesn't understand the constraint, I have to explain a little bit further. So the faces, the possible faces in the 3-dimensional cases is that you can have left face, you can have right face, you can have the front face, you can also have the, excuse me, let me erase all of this. Okay, you can have the front face, you can also have the back face, you can also have the diagonal like this, which is still vertical, but then it's kind of the diagonal like crossing the entire cube space. Okay, so the only constraint is that faces need to be vertical. And then the cap can, the cap is something that is kind of whose projection will be the bottom type, like the shape down here. So it can be just bottom here. It can also be the top, like this. So this will be a valley cap. It can also be something like this, because if you look at the projection of this red square, it will give you something like this in the bottom. So that's okay. The one that is completely vertical will only will not have this shade shadow on the ground. Dan, did I answer your question
So-
somehow?
So I think you're saying you need to have one brown face that projects to the entire green face, one and only one,
Yes,
and
And
the
the
red
red
face must also
one
be
and
there.
only one. Yeah.
Okay.
And the 4 other parts, they are vertical, completely vertical.
Okay. And then in the chat, someone asked, why do the diagonals always go from bottom left to top right?
Okay, so the question is why the guy going from here. So it depends on how you specify the direction. So so the direction I'm kind of implicitly assuming is that you're going up here, and here and here. So diagonals means that you are equating 2 dimensions. So the only possible diagonal, for example, in this, let me label them for I and j. If you're equating I and j, you're going from this point to this point. I mean, from the bottom left to the top right. So you're not going to get this diagonal, because we don't have a reversal. Like this diagonal means that you're equating the j with an inverse or reverse of I. So you can only equate in 2 things. So it must go from here to here, or from this to this, or from this to this. So that basically shows all 3 possibilities. Does that answer the question?
Yeah, I think that's perfect.
Okay. All right. So okay, let me just show you. Okay, let me show the how can we end the poll? Somehow I couldn't access the Zoom panel anymore.
Okay, so I've ended the poll. There were 5 yeses, 3 nos, and 7 I don't knows.
Okay. Good. As an instructor, I really love the diverse responses because that's more interesting. Okay. The answer is that this formula is incorrect, but I'm not going to show you the correct formula because I think it's a very interesting thing to think about. So this is actually not correct. The reason is that if you think hard enough about this, there are also maybe some problem here, but already this part is wrong. So let me go back to the slide here. The reason that we have 2 to the n minus 2 is because this part is basically the number of possible faces that you can have. Okay, so this is a number of possible faces you can have, and for each possible face, you can say that, oh, I want it, oh, I don't want it. So there are 2 to the n minus 2 choices. So that's basically the idea. But here, so I want you to pay attention to this. So this is still a possible faces, but this is not taken into account in this part at least. So already this part is wrong. And also the entire formula is wrong, but already this part is wrong. Because this doesn't take into a possibility of the diagonal faces that you might have. Okay? But I don't think it's very interesting to reveal the answer to you. I just want to tell you that this is wrong, and please figure out something cooler. And by the way, the counting itself is not really important in my opinion. This counting exercise is to make you realize the potential of the diagonal faces and also the diagonal caves and also the diagonal composition. Okay, is to make yourself familiar with this variant by understanding the full potential of this composition operator. Okay, the counting itself is not really important, but I believe that some of you will be immediately figure out the answer in the Discord. So I'm looking forward to that. But let me move on because I have other things I want to talk about. All right, so that's composition. Okay, so that's composition. Okay, so you have the diagonal cap. You could have diagonal cap. You can have diagonal faces, and you can also doing the composition to or from a diagonal, like the red part. So that's a new thing that is not really in the Cubical Agda. Okay, so let me move on. In addition to the homogeneous composition, there's a second one operator, which is the coercion. I think it's and also the transp in Cubical Agda. It's a primitive operator there. But in case that you have no idea what I'm talking about, it's basically saying that, okay, I have a type, like a square, a type square here, and I have elements on one side. So I'm going to assume that the relation goes this direction. So this is the zero side of the type, and I have a line over there. So this as a type of the zero side, and I want to get an element on the other side. So the type is continuous. So so you could do this. You could kind of transform or transport this line to the other end. So this is called coercion or transport in some of the some Agda library. And this is different from this composition we are talking about. So we have seen this variant where you are omitting all the faces and you only have one cap, and the composition will give you the other side. The difference is that for this homogeneous composition, the type is not changing when you are doing this. So this line will have, this top line will have the same type as the bottom line because, well, the type is not changing vertically. But when you're doing the coercion, the type can change. So the type here or type at anywhere might not be the same as a type at the rear. So the type can change when you're moving along. So that's why it's called coercion. You're coercing something, right? It means that you're changing something. Okay, so this is another operator. And this operator together with the previous operator will give us enough structures to make sure that we have enough passes in the type definition that we have. Okay, so, but this is not the end of the story. For different cubical type theories, we are actually having different kinds of coercion. So in the Cubical Agda, for example, you must go from 0 to 1, but you can also specify some kind of extra constraint when you're doing the coercion. For example, you can say that I want to coerce from 0 to 1, but in addition to that, I want to make sure that the yellow part is not changed at all, which means that this point, the value of this point will be exactly the same, judgmentally the same as this point when you are doing the transport. So this part will be exactly the same. Okay, you can also specify multiple parts or different parts in Cubical Agda. So I don't want to go into the details because this is not the variance I want to talk about today. I just want you to know that when you are moving along in the primitive operator in Cubical Agda, you can also specify some kind of additional constraint to make sure that some part of the beginning term is not changed after the coercion. Okay, but this is not what we're talking about. What we have, so we have different kind of fanciness. So in addition to 0 to 1, oops, let me erase. Okay, in addition to 0 to 1, you can also go from the other side, from 1 to 0, or from the diagonal. So we really love diagonals. So if you have no ideas what the Cartesian cubical type theory is doing, just repeat the word diagonals everywhere, then you'll be fine. So you can have diagonal, the coordinate diagonal to this. So you can see that this endpoint meet, which means that this endpoint, this part actually is not changed. Okay, so they will be judgmentally the same. So you're just moving this diagonal into the one, and then you can also move the other side, and you can also move a diagonal to the 0 or 0 to the diagonal or 1 to the diagonal. Okay, so you can have all kinds of variants, and that's fine. You can also imagine that in the three-dimensional cases, then you can have a diagonal to another diagonal. But I really lost my energy when you're drawing all this 3D. I hope this is already representative enough to give you some ideas that you can basically do all kinds of coercion. Okay. So this is a summary table that maybe some of you are already like looking for. So in the Cubical Agda, where the fundamental theory is paved by the CCHM paper and also CHM paper for the high enthalpy types. And so the algebra there, you have 0, 1, and mid, join, and this tilde. And the homogeneous composition there is from 0 to 1, and you have a constraint r equal to 0. And that also includes r equal to 1, because r equal to 1 can be represented as tilde r equal to 0. So this really includes everything, okay? And the coercion or transp, TRASP, has the additional feature to kind of fix part of it. Okay, so that's what you have in Cubical Agda. And in the red TT or cool TT, we have a much simpler algebra on the intervals. So this is the Cartesian cubical type theory that I'm talking about today. You have 0 and 1 and variables, and that's it. And but homogeneous composition is much richer. You have any you can go from any diagonal to another diagonal, or 0 to 1 or 1 to 0 or whatever. So r to r prime is going to summarize all possibilities, and you can have r equal to r prime. So r can be again 0 or 1 or variable. So if one of them is 0 or 1, it basically is what you have in Cubical Agda. But if both of them are variables, for example, I equal to j, it means that you are getting the diagonal. So this includes everything here. Well, that's not precise, I'm sorry. So this includes the 0 side and 1 side, and also the diagonals, okay? And the coercion can also go from r to r prime. Any questions? If you have any question, this is a very good point for you to ask, because then I'm going to ask you questions very soon.
I don't see any unanswered questions in the chat yet. We could wait a moment longer.
Okay.
Or someone could raise their hand if they want to ask something. Someone asked, I don't understand with fixation and r to r prime, the bottom row, I think.
Okay, so let me explain that again. So with fixation, by fixation, it's kind of a terminology I invented. I'm not sure how to call it precisely. So the fixation is like the yellow part here. So it means that when you're transporting, saying that this has a value 0, this will be judgmentally equal to 0 as well. After transport, that along the line will be 0 all the way. So if you look at the transp, okay, I don't really want to open up my browser during a screen share. Usually there will be some kind of unexpected tab showing up. But if you look at the transp primitive operator in Cubical Agda, you will see that it's taking an extra dimension, which is basically specifying the part that should be the same. So that's what I mean by with fixation. So the yellow and the red part means the part are being fixed during the coercion or transport. Does that answer the question?
It does, yes. Thank you.
Okay, and then the r to r prime here. So let me just label it. Okay, so this is what? This is 0 to 1, and this is 1 to 0. Oops, 1 to 0. And okay, I have to specify the direction. So let's say that the coercion direction is I, and this one is j. So this is j to 1, and this is 0 to j, and this is j to 0, and this is 1 to j. Okay, so you can also, technically speaking, have 1-to-1 or 0-to-0 or J to J, but I didn't draw them out for the same reason that I didn't draw those degenerate cases in the previous slides. But this can be summarized as R to R prime. Okay, so if you want to summarize all possibilities here, like 0, 1, 1, 0, 0, J, J, 0, 1, J, J, 1, and then this is basically summarized as R to R prime. Okay. I hope that answers everything.
Yes, someone thought you might have got the I's and the J's backwards in the picture, but I think you did have it right.
I think I'm okay. I didn't
actually
spot that. Okay, it's very possible that is a bug because my IQ is halved now, so it's possible, but I didn't see it.
Okay. Okay, let's go ahead. There's around 20 minutes left.
Okay, so someone mentioned about the fillers. So that's something cool about this Cartesian cubical type theory. So in the Cubical Agda, you probably need some actually many constructions to make it work. You can use the meet and join. You can also just go up in the dimension in a different way to make it work. But okay, I'm going into detail. That's an exercise for you to define basically H field in terms of H comp in Cubical Agda. Here we can also do the same thing, but in a slightly different way. So the idea is that you go up by one dimension, and then you do the composition, and that composition should give you the fielder. So what we want is to basically fill the entire thing, not just the top line, but the entire square. So you can go up here, and the trick is to be degenerate in this dimension, no matter what direction you have. Oh, you actually have to go in this direction. So let me call it K. So if you like the front back direction, if you just keep things degenerate at this direction, then this red square will be the fielder. And I hope that, oops, my computer is not happy with this. Dan, can you still hear me?
Yes, it's fine.
Okay. For some reason, it's eating lots of CPU now. Maybe the fielder is too cool. Okay, so so one way to do this is that you go up one dimension and you can get this. So the exercise I want to leave for you, by the way, I will not ask the Zoom question for this because this is not a yes/no question. So you have to make sure that this is indeed the original composition. In particular, you want to make sure that if you get the fielder and you get a top line of it, it should be the same as just doing the plain old composition and to get a top line. So you can ignore everything on the left and just focus on the diagram on the rightmost diagram, and then it can give you the top line, right? And you can also go through a very elaborate process. First of all, you go up by one dimension and then get a fielder and then get a top line of the fielder. And those two ways to get the top line should agree, which means that the fielder is really the fielder, not just the faces and cap, but also the composition. Okay, so I'm going to leave this exercise to you. There's a hint here, but I believe, okay, I assume that you all see the hints. So I'm going to move on. Another thing I want to tell you is that by combining homogeneous composition and the coercion, you can get the heterogeneous composition or just composition. You probably have done this exercise in the At.I lecture. Oh my God, I forgot what exactly. Oh, okay, I think it was there. And but you can also do the same thing here, but I don't want to go into details. The hint is that you probably, maybe, possibly also want to consider another dimension, but I'm going to stop here. Okay. The thing I'm going to tell you is something really outside of the box. All right, so we have seen all kinds of different shapes of this composition, or different possible shapes that the composition can have. Let's forget about these faces and cap and just think about something more general. Okay, so you have a square and then you can specify some part of it, and then you probably can ask, is there an operator to get you another part? For example, here, is it even possible to have an operator saying that if you have a top and bottom and I want the diagonal? Okay, so then could you start the polling for this?
Okay.
And I think I'll wait for, let's see, I'll wait for at least 3 minutes because I think it's interesting. And please ask question if you feel that this question is not understandable to you right now.
So the question is whether this is a valid filler?
Okay, so the question is that whether it's about filler. No, you're only getting a diagonal.
Right, so what's the question precisely?
So the question is that previously we have seen different composition problem. And let me just go through slides. For example, there are 24 of these composition problems. So you specify some part of the square, and you want to get another part of the square. And this is about what it's doing here. And I'm asking a new question. What if, let's forget about what we have already talked about, and let's just imagine a new kinds of cubical type theory or other kinds of type theory, where you potentially could have a composition problem where you have a top line and a bottom line and nothing else, and you wish that this operator can give you the diagonal.
Okay, what's the question?
And the question is this a reasonable operator to add? Okay. Is it possible, or more like this? Is it possible to have this operator? Yes, no, I don't know.
Okay, we have 6 answers so far. 8.
I think I can wait a little bit more.
12.
Okay, I forgot to start the timer, so I think I'm going to wait for 1 more minute.
We seem to be paused at 12 responses.
So the reason I want to kind of make you think about the different things is because we never believe that. Okay, maybe some people believe, but I never believe that we have the perfect cubical type theory now. And the discovery of diagonals kind of opened another door to a different design. And who knows that what kinds of weird compositions that we're going to have, and maybe that will work. So I kind of want you to think about different alternatives. That's basically the entire purpose of this colloquium, is to show you different possibilities and to force you to think about different possibilities. Okay, I think we have at least 3 minutes. So for this, unfortunately, the answer is no.
Well, should I
yes,
show you the results? So it's,
yeah, that would be great. Thank you.
5 yes, 6 no, and 2 I don't know.
Okay. Okay. So the answer is that no. But it's also beneficial to know why. Suppose that, make sure that I have the correct color. Why is it? Oh, okay, good. Okay, so suppose that you have the type is bool, or like bool all the way. Even though it's a line, I'm going to just assume that it's bool all the way, and the top is true, and the bottom could be false, because nothing says that they need to be the same, right? Before adding this diagonal, they are completely disjoint. So it's impossible to have this operator for every type, because, well, already in the bool, you cannot have a path between false and true. So the answer is no. Okay. Any question? Let me move on then. How about this? Okay, then I need your help.
You need my help?
Yeah, please relaunch the poll.
Okay.
Okay, so this is another thing. So you have 4 sides completely specified, like the bottom, the top, and the left and right. And then on the middle part is missing. But then you wish that this operator is saying that if you have like the 4 sides, and then you want the middle part to be filled. Is it reasonable to like the same game but different shapes? Could we have this? Yes, no. Okay, I'm going to really launch the timer this time. Okay, 3 minutes.
I think 3 minutes is too long. We already
Really?
have 12 answers already, and last time we only got 13 answers. So.
Okay. I guess okay. We can speed up this part, and then I can then take more questions. I think that would be more beneficial for everyone. All right. So the answer is that no. Sorry for the okay. So the answer is no. The reason is that and this time I'm not going to talk about I'm going to use a circle type. And then I'm going to put the raffle here, which means it's a constant path. Raffle here, or more precisely, it's more like a base everywhere, except the top line. Okay, so the top is loop. This is the base. Oops, excuse my terrible writing. And then the basic base is all the way here. The U shape, entire U shape is base. And then you have a loop at the top. You cannot fill this, because by filling this, you're basically saying that loop is the same as raffle. You're basically collapsing the entire circle. So this cannot have it. Okay, so in general, you cannot have this. So and I want to zoom out a little bit. So what does these 2 things tell us? It means that, well, the constraints, if you really want to have the arbitrary part out of it, then maybe they should be connected somehow. And this, the second question means that they shouldn't have kind of some arbitrary hole in it. And one sufficient condition, not necessary, but sufficient condition is to consider the contractible shapes. So this is not contractible because they're kind of separate apart. And this is not contractible either because there's a hole in the middle. And I want to go back to the 24 cases slides. All of this, if you look at the brown part, like not the red part, but only the brown part. This is a contractible shape. This is a contractible shape. This is a contractible shape. This is also a contractible shape. This weird thing is still contractible. This is still contractible. Let's see whether there's some more interesting. And this end here is still contractible. And this is even the case for the 3-dimensional cases. So contractible shapes is one sufficient condition for that. And we actually impose more condition on this to make it a sufficient condition for contractibility, and the contractibility will then be a sufficient condition for having a filler. Okay, I don't want to go into the details because remember, you can just assert different general possibilities, general possible composition. Then you also have to define these operators for every type you have, like the function type, the sigma types, the circle, whatever types that you have, that you can say, okay, now I want to consider this operator. Then that becomes a new interface for every type. And you have to make sure that every type can implement this new interface. So I'm just showing you the possible new interface. Maybe for some interface, it's very difficult to implement. And remember, whenever you want to try whether something is really possible, you have to figure out the universes, or in particular, univalent universes. Because if something doesn't work, I will go into bet that it must be the univalent universe not working. Okay. Final question. So this is similar to the previous one. So you also have all the four sides specified. But now I'm going to ask you, is it reasonable to have operator like getting a diagonal, but only diagonal, not the entire square, but the diagonal? Okay. Then I think we can launch a poll with 30 seconds or something.
Okay, it's launched.
Okay, please vote as soon as possible because we are going to review. I'm going to review the answer when I feel that there are no new votes coming in. Is that the case already?
Still changing. We're at 11, 12, 13. Okay, seems to have stabilized at 13 with 7 yes, 3 no, and 3 I don't know.
Okay, so I think we can stop the polling. All right, so for this particular thing, it's potentially possible to have this operator, but again, I didn't really check whether it's possible to implement this operator for every type you define, but theoretically it's possible. So the idea is that for this one, you can, for example, if you have this shape, you can just ignore the top face and then you just get a U shape out of it, and then apply. Let me go back to this. Apply one of these operator, for example, where is this one, the U shape, and then give me the diagonal. Okay, and then use that diagonal as a diagonal. Excuse me. Use the diagonal as a diagonal here. So you might wonder why doesn't this run into the problem that we are having previously? Well, because you didn't fill the square, so you didn't really witness a path from the top to the bottom. You're only getting the diagonal. So this triangle is not filled. This triangle is not filled, so you don't know whether it's fillable, and this triangle is not filled either. Only when you fill both, then there will be a problem. If you leave one of them unfilled, then it's potentially okay. Okay, so I'm going to stop here because this is already the last slide. So the thing that I really want to show you, so I didn't show you any code or any real syntax, and just focusing on the intuition, because I think the intuition is actually much more important than understanding how exactly you write these cubes or squares down as a concrete syntax. But also that I think this intuition or visualization or other things that you like might help you to discover new variants of cubical type theory that might work better. Okay, anyway, so I would like to stop here and go back to this summary table and take questions.
Okay, thank you very much, Favonia. We can't have people applaud in the webinar format, but they can say thanks in the chat or applaud in the chat. But I will open the floor to questions. So if anyone wants to ask a question, feel free to raise your hand. You could also put it in the chat, but you know, maybe if you want to speak up, that might be nice. I'll start the ball rolling with a question. So the sort of composition operations you have start with this brown data, and you choose a dotted red section that you want to be the output. it seems like you could also have it so that you provide the Brown data, and then the entire cube gets filled.
Mhm.
And then from that entire cube, you could extract different parts of the output if you only wanted a lower dimensional face or something like that.
Mhm.
Does that seem to work as well?
That's definitely working because you can, well, excuse me, you already have this, and it's also not hard to go the other way.
Mm-hmm.
Yes,
So
you described.
the idea would be that the sort of data you have to provide is a little bit less, because you don't have to say which face you want in the answer. You just say, give me a whole cube from this Brown constraint.
I think in terms of syntax, okay, I have some personal bias here because technically they are the same or equivalent.
Mm-hmm.
It's just that I think I have slight bias because if you only get the composition, then the filling direction. That's great. Maybe let me use this one then. Okay, so if you're getting the entire thing, then you're getting the square, which means you also have to the filling dimension will be exposed. The vertical dimension will be exposed. If you're only getting a line, then you're basically you start from lines and you get a line in the end.
Mm-hmm.
And that seems to be practically more pleasing, at least to me.
But you start with the Brown data, which includes a vertical coordinate as well. So you need two interval coordinates for your input data.
Right, but that part can be then be bound variables inside of the facet part.
I see.
And so the output of the entire composition does not involve that bound variable. For the filter, then you have to make sure that there's a kind of outside kind of filling direction up there.
Okay.
I mean, it's doable. Like I don't want to say that it's impossible. It just
It just seems like usually when you do a composition, you'd also like to have the proof that it's a composition, which is the higher dimensional triangles or squares.
Mm-hmm.
You often want to have both data at the same time, and you showed a trick to get that, but maybe it might be natural just to provide the composite and all the commutation regions as well.
I see. I mean, that's a valid point. I just want to point out that in Cartesian cubical type theory, it's almost like trivial to go back and forth.
Yeah.
Because of this construction. So okay, I don't have a good answer. I feel it's more like a personal taste.
Anyway, the real answer is it's equivalent, which is good to know. Okay,
Yeah.
how about other questions from the audience? Anyone want to raise their hand or put something in the chat? Okay, well, I don't see anything, so I'll just thank Favonia again, and then I will stop the recording.
Okay.